Hi everyone, I'm Cody Rue and this is the Church of Logic. Today I'm going to talk about real closed fields. What's real closed fields? Well, basically it's just a bunch of operations and axioms in first order logic. So as I've explained, in first order logic, you can add certain functions and they can take, some number of inputs, 0 if they're constants, 1 if they're unary functions, 2 if they're binary operations. And then we can add a bunch of axioms over those, like for all x, x plus y equals y plus x. All right, that's an axiom that involves, for all. Actually, I should have said it for all x and y, but it involves a for all and it involves x and y in this binary operation I called plus. So real closed fields is exactly like that. It has binary operations. It has plus, it has times, and it has a binary relation, less than, and then it has the usual equality. All those axioms of plus and times are very standard, unsurprising axioms. X plus y equals y plus x. Multiplication is distributive over addition. X times 1 equals x, stuff like that. And you also add division just to make it a field. And we're trying to make this as much as the reals as we can. Now, this is first order logic. It's just a theory with axioms, right? We can't really say, oh, just take the usual construction of the reals, because that doesn't really make sense in first order logic. But you can say, okay, well, what do the reals satisfy that we can talk about in first order logic? Well, we know that the squares are positive. And in fact, we know that every positive number can be written as a square, right? Basically, you take the square root of that number. Of course, negative numbers don't have square roots in the reals. We could sort of try to extend this theory to talk about the complex numbers, but we're not going to do that for now. And of course, we're going to, if you want an ordered field, that can't have square roots of negative numbers. But okay, so we've added a bunch of axioms. Are there any left? Well, yeah. What about cube roots and fourth roots? Actually, you sort of just want to say, hey, really any polynomial that that crosses, if you graph it and it crosses the real line, that thing should probably have a root, right? And the way you say that is just by writing down every single axiom, an infinite number of axioms, all of the form if I have a polynomial, right? So a certain coefficient times x to a certain power, which is really just x times x times x, that number of times. If I have a polynomial and it's odd, its degree is odd, then really that thing should have a root, right? So if I have 2x cubed plus 3x squared plus 4, that's an odd polynomial. I know that at some point it's going to cross the real line, right? It can't stay above, it can't stay below because it's odd. And so, either at, minus infinity, it's going to go to minus infinity, and then plus infinity is going to go to plus infinity, or the opposite, right? It starts at different corners. So it crosses the line. So you just say, okay, I'm going to add all the axioms that say these things have zeros. Great. Okay, so we have this kind of complicated first order theory, and it has an infinite number of axioms, and it might be worth wondering, okay, what is this even good for? Well, here's what it's good for. Something remarkable transpired in the early 20th century, where people were kind of reeling from these incompleteness theorems, and they noticed, wait, this theory actually is complete. It doesn't suffer from the incompleteness theorems. And in particular, that means everything that I could possibly say in first order logic that concerns the reals, in this theory, I can decide. This theory either proves the statement or it proves the negation of the statement. Right? So a kind of miracle occurs where this theory just happens to be complete. It happens to capture all the true things, right, within this first order theory. Now, of course, the incompleteness theorems are still true. It just means that this theory isn't expressive enough for the incompleteness to apply. And this might seem a little surprising, and maybe I'll talk more about this later, but it's a little surprising because, you'd expect the reals contain the integers, and I went over some detail that basically any theory that really knows how to talk about the integers is incomplete, cannot possibly be a complete theory. Now I'm saying this thing that seems bigger, this thing that has all the reals that it talks about, is actually complete. And the lesson here is that appearances are deceiving. What really is happening is it turns out the reals, despite being bigger intuitively, are actually a simpler theory. And it also means that we can't possibly take this theory of reals closed fields and generically talk about integers, right? We can write each individual integer, right? We can write 1 plus 1 plus 1 plus 1. And that'll be the integer 4. But we can't say, we can't quantify over x and then somehow express that x is an integer, right? When we quantify over x, we know that x is, somewhere in the real line. But there's no way to express, but actually this real number is in fact an integer. I'd invite you to think about that for a minute. Just think about how you try to express that x is an integer in first order logic using the language of ordered fields, right? You can talk about x less than y. What you'd be tempted to say is, well, x is 0 or x is 1 or x is 1 plus 1. But of course, you see that would be an infinitely long statement, and we don't allow those. So now you try something like, x is, the root of a certain polynomial. Maybe that polynomial is linear, but you'll see that you run into trouble. Basically, you can't talk about the integers. All right, but let's explain this miracle a little bit more. Why could it possibly be that the real closed fields is decidable? Well, one thing that you can notice is that we have good algorithms. We have ways of checking whether a polynomial has a certain root in a certain area. I'm not going to go into too much detail because I'm already running out of time, but one thing that's cool is, at least in one variable, there's this pretty simple algorithm where you give it two bounds, right? Say 0 and 1, and you can just calculate how many roots a given univariate polynomial has within those bounds. There's just a simple algorithm of algebraic manipulation of that polynomial that just tells you, there's no roots within 0 and 1, or there's 5 roots, right? It just tells you it's a very simple, it's a comparatively simple algorithm. So, one of the miracles, like I said before, is that this extends to higher dimensions, right? You have two, a polynomial in 2 variables or 5 variables, and we can sort of give these regions where we say, hey, this polynomial is always going to have this sign or always have that sign. And then you break it into a finite number of regions. And then basically you can take you can take a statement in the theory of real closed fields and then just check it at a single point within these regions. And that will say whether it holds for the whole region, right? So if you can divide the whole, n-dimensional space of your variables into a finite number of regions in which you know that a single point in that region will determine the whole truth value for the entire region, then you've reduced this kind of difficult problem of deciding, whether a statement is true to just checking a finite number of things. Now, I'm talking about decidability, even though I started by saying completeness. One thing that you should know if you listen to my incompleteness is that completeness actually implies decidability, right? If a theory is complete, that is, it proves every statement or its negation, it's pretty easy to show that the theory is decidable. Basically, you start looking for a proof or a disproof kind of in parallel, and then whichever finishes first, well, that's your answer. And you know that one of those two is going to finish. Of course, in practice, in the theory of real closed fields, you get first an algorithm for deciding whether that statement is true, and you use that to prove completeness. Basically, you have an algorithm where if you put in a sentence of the real closed fields, you just run it, it will tell you whether that sentence is true or not. And that is basically, the algorithm is the proof of completeness. The fact that there's such an algorithm, it's going to answer yes or no. So, okay, just to finish off, I'd like to take a beat and say how cool this is, right? There are some really complicated and subtle problems that can be expressed within this language, which we know is decidable. One example is the kissing problem. You take a sphere and you can ask, okay, let's imagine this is a perfect sphere, it's perfectly rigid, and we try to pack around it a number of spheres that are all touching it, right? That's why we call it the kissing problem. We're kissing this sphere with other spheres, and we want to know how many we can pack maximum. If you try this at home, I don't know, with tennis balls or something, you'll see that it's somewhere between 13 and 15. But actually proving what number it is quite hard. It was an open problem in Newton's time. And, you can observe, this is just a problem in real closed fields. You can express as a first order logic statement this problem. Now, does that mean you can solve this problem automatically because you have, a decision procedure for real closed fields? Well, unfortunately, the algorithm is quite slow. So even though in theory you could just run the algorithm and it would say, hey, this is how many spheres you can pack around a given one, you might have to wait a very, very, very long time. And so in general, people need to be a little bit more clever. But at least it gives you this kind of horizon of, hey, this problem, all these interesting problems where we're reasoning about space and spheres and shapes, these problems can be turned into things that are decidable in theory. And then we can start looking for algorithms that are more or less efficient for them. I think that's cool. And I think it's cool to remember that despite the sort of horribleness of incompleteness, we still have these decidable theories that talk about really interesting things. And we can think about those and put those in computers and play with them. All right. We'll talk more about this next time. Until then, take care.